Greetings and welcome to Chemistry in the AM. I'm your host, Mr. Sindelka. Big shout out to Tristan, our badminton guy, and Sarah Perch. Anyways, we're just going to start on this. We did a quick review of what we've seen. Give the Lewis diagrams, the dots that show only the outer row S and P electrons. We'll take it up in a second. I'll pause. You try this too. Okay, we're back. Talking to the machine and you. Carbon is in the 14th group. One memory aid is 10, subtract 10 from the group. However, carbon has 2 S and 2 P electrons in its outer shell. Those are the valence. 4 valence electrons. So you go 1, 2, 3, 4. Nothing doubles up. Nitrogen is 1 over from carbon. It has a total of 5 valence electrons. You look at the periodic table and figure it out. 1, 2, 3, 4. Now we have to double up. 5. Oxygen. 6 valence electrons. 1, 2, 3, 4, 5, 6. Neon is at the end of the row. It has 8 valence electrons. Everything wants to react so that it's got the more stable electron configuration like neon or the other noble gases. And it's going to be a full deck. 2 on everything. So if you want to double up right away, you can, or single, 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 double, double. Everybody's getting married? Okay. That's what it should look like. Now question, I left out fluorine. I went C, N, O, skipped F, and went to neon. But if I did fluorine, it would have been right in between here. It would have been 7 valence electrons. Now here's my question here. Any group 17 element, whether it's fluorine, chlorine, bromine atom, or an iodine or aspartame atom, how many valence electrons? 7. So the Lewis diagram for any, so if I just use a letter that's not used for anything, X is not, so Xe is xenon, but just X here, what I'm doing here, is just like a generic element for group 17. I don't mean anything in particular. Any group 17 element will have 7. 1, 2, 3, 4, 5, 6, 7. Now if I said anything from oxygen's column, 16th group, so sulfur, what would be the only thing different if I asked you to do the diagram for sulfur compared to oxygen? What's the only thing different from the dot diagram? The letter S, yeah. The dots are the same. Now, the reason why I bring this to your attention is columns are called families on the periodic table, and they have similar characteristics. Group 17 elements tend to react similarly because they just want to get one more electron. And they all react in a way that they form bonds with one other thing in general. There's some exceptions and stuff. Oxygen and sulfur are similar in reactions because they want 2 bonds. They form similar compounds. The families have some similar characteristics, not all. Now, copy this down. What is a covalent bond? It's a form between 2 nonmetals that are sharing electrons. Molecules have covalent bonds. Copy that. So, covalent bonds are found between 2 nonmetals. They share electrons, and we call those compounds molecules. Now, it's important. We only use the word properly, molecule properly, if we're talking about those kind of compounds. If we're talking about sodium chloride, sodium is a metal, chloride is a nonmetal. That's an ionic compound. It is not a molecule. It has ionic bonds, not covalent bonds. So, nonmetals, covalent bonds, call those molecules. Okay? Now, we're going to just take a look right away about Lewis diagrams and molecules. And we're not doing any ionic compounds. Now, jot this down and we'll try these examples here. I'll just pause for a second. Now this is a small enough molecule, H2O, 3 atoms, 2 H's, 1 O. I hope we recognize that that's what the 2 represents, 2 H's. Each H, and I'm going to use different colors just so you can see here. So 1 H, I'm going to say, I'll put the dot here. Would it have mattered If I put the dot on the side, no. As long as it's only one electron and we understand it only wants to be like helium and have a second electron to pair. So I'll put the other H. I don't care if I put the dot here. I could put it here, I could put it here, I could put it on the top. It doesn't matter. But I'll just put it here for you. If you want, you can put it there if it makes you feel better. I don't care. The oxygen. 6 valence electrons we added above here. 1, 2, 3, 4, 5, 6. That's how the numbers go. Now, everything wants to be like their closest noble gas, generally 8 electrons, with the exception of hydrogen, because its closest gas is helium. It only wants 2 electrons. How many bonds does this oxygen want? 2, because there's 2 lonely guys. Okay. Now the way I drew it, pardon me, there's an empty space here, and an empty space there, right? Now, pardon me, I'm thinking that I can solve some problems if I take this guy and his electron, and they kind of bond there. Now don't draw this. And this electron here are shared. Now, I'm thinking that, eh? So the way we're going to draw it is, instead of using the dots though, we're going to use a line to represent the 2 shared electrons in a covalent bond. So, I'll draw it with the same orientation. That O will have a bond between one of the H's and a bond between the other H. But that O also still has the pairs, and they have to be shown. Okay? This is what we call the actual diagram of the molecule. I was showing what atoms we're working with first, just so you realize, okay, oxygen needs 2 bonds. Hydrogen only needs 1 bond, and they solve each other's problems beautifully. Okay? Now you look at this. As far as the oxygen is concerned, between sharing and what it possessed in the first place, it's associated with 8 electrons. 2 here plus 2 here. The bond represents 2 electrons that it's sharing, one of them. It doesn't outright own them. And it has access to these electrons here. So 2, 4, 6, 8 electrons surrounding the oxygen, although it doesn't truly possess all of them. The hydrogen is happy because it only wants 2 electrons to be like helium. And both of them are identical. 2 electrons in 1 bond. It's associated with, it's sharing the second electron, so it's good too. So, now, we only learn to do by doing. It's easy when I'm doing it. You just see. Can I get you guys to try, with trial and error, these 4? Now, H2, you can have it bond to itself. I would advise you still to start out though thinking, you don't have to draw 2 H's necessarily, but each H wants one of those, and then draw the molecule. Hey, what would this look like, guys? We could do this one real quick, I think. H, and then the other one wants, I'll just draw the same color. They each want 1 bond, and they have 1 electron to share, so what are they going to do? Solve their own problem, right? How many bonds? 1. No leftovers, because they only want us. So this one will be quite simple. No leftover electron dots. Now, draw the N. And since you have, for NH3, since you already have the H drawn above, I think you know what you're looking at with H's. But draw the N. It's in the 15th column. It is 5 valence. I'll pause. NH3, by the way, H2O's proper scientific name is water, right? There's another compound like that where it doesn't use like dihydrogen monoxide or something like that. That's wrong, actually. Water is the correct name. This is another molecule like water where we use the common name as the official name. Do you guys know what it is? I said it a minute ago. Ammonia. You know what Ammonia. Ammonia is used for or smells like? It's Windex, for example. So this is ammonia. And the nitrogen wants 1, 2, 3 bonds, and luckily we have 3 hydrogens, each one in a single bond. So I think you could probably see that most likely this nitrogen is the central atom. And I would draw it like that. I hope you did too. I don't care, by the way, if you had your, if your hydrogen was at the top or something like that, and your ammonia, or if you drew it like this, well, the letter N would have been made appropriately, not Z. But anyways, it doesn't matter that. As long as you have a lone pair, 2 electrons, and then 3 bonds to hydrogen. H2O2. Now, you might have had to think about this a little bit. Hydrogen's a dead end, meaning it can only bond once, nothing else will bond to it. So I hope you're thinking hydrogen has to be at the end of the molecule. So the 2 O's must be bonded together in the middle. O, O, O. Then, if you kept it sort of like this, you might have drawn it like this. Does it have to be drawn exactly like that? No. I could have went like this. This is one other possibility. As long as you have 2, don't redraw anything. You could have had one going hydrogen up, one going down. Like you could have had, instead of here, you'd have a lone pair there. And then this one going up. Like, as long as you have 2 lone pairs of electrons on an oxygen and 2 bonds, you're good. They're equivalent. And more about the 3D structures as we go on. Now, OF2. When I see the O, I know it can bond twice, so it must be in the middle. I'll draw it the most likely way you drew it. Doesn't mean you had to have drawn it this way. There you go. Okay? Make sure that your electrons are always going like this, as in a box kind of thing. I would not mark you 100% if you went like this. And then you put your electrons like this. Don't do that. Okay? I don't like showing errors, but every once in a while somebody makes that error, so don't do it. Okay. Now, we're going to use a model kit to build these molecules and draw 3D structures. That's, I'll pause this. Obviously you can't see the model kit if you're on here, so I'll just, okay, we built models, now we're going to go to double and triple bonds. An oxygen. You guys probably remember from our previous examples, how many bonds does one oxygen want? 2. So, I'm thinking this oxygen can solve its own problem. If this oxygen and this oxygen each want to bond twice, why don't they bond to each other? That's a double bond. How many pairs of electrons are left on each oxygen then? There's still the double. So 2 here, 2 here. Now, that's based on this, right? One oxygen wants 2 bonds, it has 2 pairs. This is a linear molecule. Two things can only be connected by a line, right? Now, we said that most atoms, other than hydrogen, it wants just 2 electrons to be like helium. Most want to be like the closest noble gas, 8 electrons. Looking at this oxygen, is it associated with, maybe it doesn't possess them, but is it sharing and owning at least 8 electrons? Yes. It's got the 2 plus the other 2. It's sharing, and those represent a total of 4 electrons per oxygen. Then when you look at this guy's perspective, it's just the mirror image. He's got access to 8 electrons total as well. So it's a good structure. You'll find, and I won't do it here in the high school class, but in university, you'll have systems, sometimes they're called an expanded octet, stuff like this, where you have things add up to more than 8 electrons. But I won't get into those exceptions. Now, nitrogen each nitrogen alone wants 3 bonds. So what do you suggest we do when we put 2 nitrogens together? Triple bond. Okay. So nitrogen, nitrogen. It's still got the lone pair. I could put them on the sides. I'm doing that because that's most likely where they are. They're repelled farther away. If you put them on the top, though, for a Lewis diagram, the geometry doesn't matter. So there's your triple bond, and you see the reason why you would have a triple bond. So, I want you to try, take a minute. These two almost look like the same formula, C2H4, C2H2. Now you know you can do double and triple bonds as well as single bonds. Try those out, and we'll take them up and see what we get. It's trial and error. Okay, I'll look at A. 2 carbons, 4 hydrogens. Now, I know a carbon wants 4 bonds possible. Now, I look at this, and I think, well, carbon at least has to have a single bond. And then, if I put H's here, H is here, I have a problem, don't I? I've still got this electron and this electron, right? What can we do? Double bond. These guys are going to be shared, but I don't do it like that. I do it as another stick. Double bond. That works. Hey, you might be wondering, I've got my H's going down, like Sindelica does. You had your H's going up, that's okay. A Lewis diagram doesn't give the geometry, like the actual angles and stuff like this. If you were to get the angle better, I'll just quickly erase this, but you don't have to right now. But I'd say, okay, double bond, then there's 2 available. As far apart as can be would actually be more or less this 120-degree angle. You don't have to redraw it right now, but you'll get used to seeing this. Okay? Now, the other one, H2, that probably distributed evenly means a carbon and a hydrogen on the left, a carbon and hydrogen on the right. So we'd have to use a triple bond. 1, 2, 3, and then the 4th bond here, the 4th bond here. Does that make sense? See if you can do this one here in the next minute. I think you can. Darn too. Carbon's a useful one because it can bond 4 different ways. And I'll see here, but I hear double bond. So what goes in the middle? Carbon. Okay? Now what? Double bond, O. I got 2 pairs left over. Make sure you have those. Double bond O. That's carbon dioxide, right? It involves 2 double bonds. This should be a line too, a straight line, like, because as far as the carbon's concerned, this set of 4 2 bonds represents 4 electrons, right? 2 in each. Those electrons and these electrons involved in the bonds want to be as far apart as possible, so that'd be a straight line, right? This is actually a linear molecule. Okay, now, with the last 3 minutes, we already did NH3, so skip B. Just jot those down quickly, and we will see. Now, you could do NH3 again. I didn't realize that when I was creating these notes that I had already done that. Okay. H2S, CH4, NH3, HCN. And then you can call it a day. We're going to take them up at the start of the next class as a warm-up, okay?